Good morning, all of you. This week we have syllabus of errors, significant figures, then screw gauge and vernier calipers. Stefan. All are very small topics, and you can say a lot of some general things here. So rather than say some like, not like some in mechanics what we study topics, core ideas, very generalized applications it will come. And it is related to the total science, not only for physics. It will come in chemistry, it will come in biology, and more in engineering. It is more used in the medical science, especially errors, significant figures in that one. Because any small error in vaccine, oh no. So how come error in vaccine? Yes, it is. A small error in production of vaccine, no, it will have huge impact here. So even in the surgeries. So what all that medicines know, so they should not have any error. Error should be minimized here. So what will happen? We are going to bring a science involved in the errors. How to minimize errors, that one. For that, what is the science? We are taking help of the science, or we are taking help of the mathematics, you can better say. Or we are going to introduce a techniques. That's what the errors here. Then again, sometimes you might have seen, no, when you see the SC Verma, the answers will be given like this. It will feel, no, sir, 30.00. What is there in that? Just write only 30, or you can see some mains numerical type, no, where answer 30, you should write 30.00. Why that 00? What's the use of that? What do that 00 indicates? Is there any meaning for these zeros? Are you getting, no? So you might have observed in the mains, especially numerical type, it was of this kind, no, 00. It looks very funny, no? So 30 answer, again we have to write 30.00, or it will be like this. Well, why can't only 0.1? Because this will be more flexible. Yes, we do have certain rules to express answer like that only. That particular rules, what happened, we are going to explore it. Okay, this is about the significant figures. Errors is like always when we do any experiment, there'll be errors. How to minimize that error? After that, we'll go for units and dimensions. With the help of units and dimensions, how do we can take help of that idea? So already you might have come across many physical quantities, and for that units are there. So further, if we focus on units and the dimension, no, any use of that. So for example, impulse, that one. So impulse, what is the unit we write it? Force into time. It's also having another unit, no? Newton second, like a kg meter per second, per second, that one. So like this, how come a given quantity having two units? So if you look at the Newton second or kg meter per second. So what is the meaning of this? That we are going to explore in units and dimensions. Next, we have an instrument called as a screw gauge and vernier caliper. How to do accurate measurements, like how to measure the length, diameter, all. So this is all what happened we are going to discuss in this week's syllabus. It's a very generalized topic here and can be related to any of the physics what you learned. Any of the physics. I can this introduce in gravitation, rotation mechanics, friction. So be alert. There's nothing called like it should be asked only as a theoretical one. No, I can mix with any other numerical also. Okay, in that series, so let me start with the errors first, that one. So here we have, what is the error? The basic definition. Error, we say like it's a difference between true value and measured value. The difference between true value and the measured value is an error. It's a difference, I'm telling, not something like a true value is greater than what. The difference between true value and measured value is called as an error. Now, sir, why you are saying true value? Suppose at a point, like a length of the rod. So what is this length of the rod? It should be how much? It should be around, say, like a exact length is 10 centimeter. I'll measure with a scale 9.8. I'll measure with another scale. It may read more than that. So is there any difference between the true value and measured value? Yes, it is. So that's what error. Or the G at a given place, 9.834. And you are going to do lab, you're going to do experiment in a lab, and you are going to perform, and you are going to get answer as say like a 2, 3. Is there any error? This is a true value. This is a measured value. Another student does, his experiment will be 9.845. Look at this measured value. This is less than true value. No, what about this one? This one greater than true value. So like this, there's the possibility is there. The measured value can be greater than true value or less than true value. So therefore, altogether, the difference between true value and measured value is an error. Error based on this what can be positive or negative. With the measured value greater than true value, error will be negative. Measured value less than true value, error will be positive. So this particular error can be positive or negative. I'll just keep on write things because this topic is all about like some general information. Then we'll enter into the numericals. Okay, this particular error. Now what is all our entire science, entire engineering? It's all about minimize this error. It's all about minimizing this error. So we'll classify the errors. Errors again, there are two types are there. First one, systematic error. Next one is random error. The name itself is says no. Systematic, random. So like is doing random preparation. What do you mean by that? Is doing random preparation. What do you mean by that? We are not sure how he's preparing, but is preparing. Is doing systematic preparation. As we know, he will get up morning, he will read, then what all, he will write teacher notes very clearly. Then he will write all the points without missing. Then what happened, very important things he'll put in a box. Okay, that one. After that, again, what you'll do, you will revise things and you will put a like a weekly plan. Okay, every week, what happened, half an hour, I should revise all the things what I learned before going for exam. There's a systematic plan. What do you mean random error? You will write notes. Okay, how he writes notes, what order, we don't know. With that one, where what is the method he does, we don't know that one. When he writes, we don't know that one. Anything, but what happened is preparing. So that's called like a random that one. Okay, now we'll define one by one. The first I'll start with the systematic error. Definitely, our country is very weak in this error analysis. That's why our products are not, you can say that worth to be bought. If you look at the most of our products, no, what happened? The other countries, well, Western countries especially, they don't accept it. The reason for that, we have not done error analysis much, or you can say that the science involved in error, we are unable to utilize it properly. Because any product, suppose a mobile, what you manufacture, again will be tested forever. The software, any product or no, should be systematically analyzed for error, and it should be minimized here. So we don't have enough technology and the procedure to really minimize errors. So that's why the products will become very poor. Quality will come down. So everyone will manufacture mobile, but it's a good example. If you start using mobile within half an hour, it gets eaten up. What is the problem? The random error. That's all. It was not designed keeping random error in the mind. Okay, the fan, what happened? Even if you put for number 5, still the speed is not very high. So it's a random error, not designed properly. So it matters a lot. For engineer, what happened? This error is what? What is error? So shall I, for engineer, what you should call is a best enemy, ever enemy, that one. Your whole profession, what happened? Every day with whom you will be fighting with error. Not with your colleagues, not with your competitors. The error is what happened? You take any engineering field, this, what is the biggest troublesome for you? Error. How much you minimize error, that much what happen, you will become popular or you'll become good engineer. So it's so challenging for engineer that it will really kill him, this error. I'm telling this one. So as we enter numericals, you can see that. Especially random error. Okay, first we'll focus on systematic error. To be frank, 20%, like 80% of resources are consumed to minimize error. 20% is what? To construct, to design, to plan, design, manufacture, everything will come. Different. Remaining 80% will go in only what when minimizing error only. This will take a lot of resources. The 20% is what the product. We are able to manufacture product. The remaining 80% of resources are what? For minimizing error only, it will take that one. You just imagine, means you're constructing mobile. So how much, like a 20% is what resources, 80% is what resources are meant for even the testing only. To ensure quality, that one. Okay, these are the challenging things what we have, we are encountering. Okay, systematic error. So these are first thing. The cause is known. The cause is known. Are reproducible. Means they'll get repeated, reproducible or gets repeated. Or positive or negative. There'll be positive or negative, or it's like a one-sided. Either you do that experiment, if the systematic error, it will be always positive if the error is positive, or it can, if the negative, it will be negative only. It cannot be for one value positive, other value negative and all. Either positive, or positive or negative. I'm saying not like a maybe. I'm saying that one. If it is positive, it will remain positive. If it's negative, negative, or one-sided. This one. So this is. Like how to, like these are the causes known. So I know exact cause why it has happened. They are reproducible. They get repeated again and again. You do any number of times, they'll get repeated. And if you minimize it, they'll get eliminated. Can be minimized and eliminated. Okay, this is some general thing. So what is the reason? This, you can select a poor accuracy. What do you mean by accuracy here? Suppose say the value of G is say 9.854 meter per second square. One value will come, which is say like 9.743. So what's the problem? Accuracy is the problem. No? It is very far away from this another value. Okay, let's come for this one. So this is what you can select a more accurate and precise. What about this? Less accurate and less precise. This is less accurate and precise. What do you mean by precise? Accuracy is like a precise means what about decimal places? Up to 3 decimal places precisely you are expressing. No, we say no, precisely means up to 3 decimal places you are expressing answer. What about this? Yes, precisely we are expressing. Okay, it's having how much precise it means how many decimal places you are expressing. Those many decimal places I'm expressing. So shall I say this is also precise? What about here? It's a less precise here, no, and a less accurate. You can see 9.8 is needed with this much here. And what about this? This is what happened, 9.853. Yes, it is near to the measured value. So, so this is a true value. This is a measured value. So look at this one, the third one. So what it is accurate, no? And also more precise. What about this? Less accurate and less precise. So I can also give example where it is accurate but not precise. So 9.9, almost it's near to that one, no? So what is the problem with this? Accurate but not precise. Okay, all of you getting the precise. Precise means like it's about the decimal places. The true value is having 3 decimal places. What about the measured value? So how many decimal places it is having, that will determine the precision. So what about here systematic error? It occurs because of poor accuracy. Poor accuracy, that one means the more the difference between true value and measured value, it is more, you can say like accuracy is very poor. What about the precision? Precision about the decimal places. Okay, no, result is, so what is the thing? A result is said to be accurate if it is relatively free from systematic error. So what is the meaning of this one? A result is said to be accurate if it is relatively systematic errors here. Okay, fine, this one. Now, can be positive or negative or one-sided, can appear on either side of true value. I'll write down all the things. Huh? Both the third point and the what I'm writing are same, can appear on either side of true value. So sorry, like no, can appear. No, this one. It is for random error. Huh? It's actually it's like a will or more often on one side of the true value. No, average ever, average ever stays the same. Means you take the average, you take the uh, error in all the observations and you take it average, no, it will same that one. Average is same. Results are limited by accuracy. So how do, and error, I'll write it only. The systematic error is managed by careful experimental design and manufacture. I think I'll action this here. There's a thing. Next, again, one more. Okay, we'll have there's a true value. Huh? What about the measured values? The measured value will be like this. They'll be lying here. they'll be on one-sided. So why do that deviation? Actually, what happened, the blue color line, red color line should merge, but because of systematic error, they'll get deviated. And they'll be one-sided, either on the left side or right side. So here I wrote somewhere here, are often on one side of the true value. There's the meaning that one. Okay, fine. So this is about the systematic error I'm introducing. Okay, let's see that what are the types of systematic error. Okay, let's see that. What are the types of systematic error, so that how to minimize them, we can see that. So types of systematic error. So first one is instrument error. So instrument error is nothing but what you can call like a failure to calibrate. What do you mean by failure to calibrate? Suppose a scale 1 centimeter, 10 divisions should be there. In that, instead of 10 divisions, if you make it 9 division, you didn't calibrate properly. I'll write all one by one. I'll give the sufficient. If this is scale, what do we expect? We expect like there's a 1 centimeter. 2 centimeter. So this, instead of marking how many divisions are there, you calculate 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. In 1 centimeter, 10 divisions are there. Instead of no, sir, I'll make it 8 divisions. Then you have error. So there's a true scale, means a scale without error. A scale without error. So now I'll say that I'll manufacture a scale where errors are there. Another like a who is not having any knowledge of tell me like a who is right. There's a true measurement, there's a true scale. This what manufactured scale. Is there any error? Yes, definitely. No. What is the error? Will it read more or less? It will read less. No. If you take an object, suppose that there's a rod is there, you keep it here. So there's a length of the rod you want to measure using this scale, and it will read 1.5 centimeter. Am I right? Then your scale, how much will read? 0.8 centimeter. Suppose you are measuring gold. Suppose like a gold rod, you are going to purchase it. Then what happens? You have a shop. Okay, that one. The length of the rod. For every 0.1 centimeter, you are charging 10,000. Tell me like, will you be on loss or gain? I think better I'll leave it to student. So what is this problem? Manufactured scale. So is there any error? Yes, that one. There's an error. So why this error has come? Because failure to calibrate. Not markings are not done properly. This is called like a failure to calibrate. Like that, we do have many things. Not only I'm giving scale, like that calibration, something becomes very, very important. If it's not properly calibrated, then definitely some error will come. This is the meaning of failure to calibrate here. Next again, there's the first one. Degradation of parts. So as you start using it, there'll be degradation will come. Degradation of parts means as you start using, suppose say, uh, best thing degradation. So we can take to measure the length particular thing what happen. So this degradation will occur. No, so degradation means this particular markings will not be visible. Suppose I think if you take the geometry box scale, when you use this for 1-2 years, this marking will get vanished. No, nothing but failure to calibrate or degradation of parts it will come. Okay, getting this one. Next again, the instrument itself, what happen, the thickness or its size, what happen as you constantly use, what happen, its parts, what happen, their size will come down. And because of that, what happen, definitely the degradation of parts will come. This is why degradation of parts due to constant use. This is a natural thing. Then what you should do, bring it another new one because you can't again set right things. No, there's a degradation of parts it will come due to constant use. Next again, third one, power failure. Okay, degradation of power failure. So what is the power or power fluctuation? Sorry. Some of the instruments open, they work on the power. Due to power fluctuation, they read some other values, especially electrical, electronic equipments, which work on the power. No, due to fluctuations in the power, they will give the different readings. So there's a most probably noticed in, most probably noticed in electrical equipments, electrical and mechanical equipments. Okay, now after this, zero error, instrument error is one more. A good example is zero error. So of all this, so if you look at the scale, especially meters, no, they'll mark zero here. This will become zero, no, 0, 5, 10, 15, 20. So when you are not using that scale, where zero should be, where the zero should be, the zero what happens should exactly lie at this particular point, no. The zero, when there is no reading, when there is no measurement, so where the zero should lie, zero, zero, the pointer should merge with the zero, no. But practically what will happen? So sometimes what happen, the equipment the zero, the pointer will not be at zero. Now, what is the problem with this? I'll draw some better diagram. Okay, able to means when equipment not in use. When equipment not in use. So where the pointer should be, the pointer should be at zero, no? So, but it is coming here. So it's a zero error. So what to do now is I have some like a screw will be given where I can bring the pointer back to zero. Okay, and weighing scale, nothing is there on the weighing scale. It should, distal weighing scale should read zero, no? So therefore, what you do that one, if it's not zero, that one inside what when there's some screw will be given. With that screw will adjust and will make it zero. This is called okay, zero. When equipment is not in use, the pointer should be at zero. If it's not at zero, then it's said to be, there is a zero error is there. Okay, third one, This is about all the instrument errors it will come. There's not well defined. We are just listing all the things. Calibration error, failure to this is called like a calibration error, failure to calibrate or calibration error, degradation of parts due to constant use, power fluctuations, zero error. Next again, temperature fluctuations. So due to variation of temperature, suppose if you're using metal scale, so as you increase as temperature increases, then the scale will elongate, so it will read error. So like that, even the temperature fluctuations, variation in temperature. So this will lead to instrument errors. So the instrument what happen will encounter all these things. I have listed only few, still plenty are there. Degradation of parts is something very, very important. Remaining all we can manage. Remaining all we can manage. The degradation of parts is something unavoidable because the size of, due to constant use, the size of the dimensions of the parts will what happen? Will decrease or increase depending upon that one. So that will cause a lot of error. That is, this about the first one is the instrument error. Now next is imperfection. First one we made, no? Instrument error. Systematic errors, these are all parts. No. The second one will go for imperfection in experimental techniques or procedure. So the best example, I will take screw gauge because everything. Oh, so like this one, simple pendulum. You all are aware of that. Okay, there's a simple pendulum. There's a bob. There's a string. No. No. How you measure time period of this pendulum? There's a length L having a mass. So what we are going to do? We are going to release it. You're going to release it, and the moment you release, you should start counting time, no? And it's going to oscillate. Okay, no, what are the things we do here? Okay, let's try to such imperfect in experimental techniques or procedure. The first thing when we are working on this, what are the things that one? The tension will act, the weight mg. Due to air, there'll be buoyancy. This buoyancy will neglect. And when it is moving, there'll be viscous drag on it will be there. Velocity, this will be say like a T1, there's a V1, mg, buoyancy, and there'll be viscous drag. We do neglect this viscous drag, we do neglect this buoyancy. All this will become imperfect, no? When you're calculating time period, you should consider all these things, but we do neglect here. Tension, I'll write T naught, again you'll get confused with. So next again, the bob will spin, it will have a wobbling effect. There'll be friction at this particular point. At the point of suspension, the string, what will happen, will expand, will elongate. There'll be wobbling effect, there'll be twisting of, elongate and twist in string. Bob also wobbles. So do we consider all this nothing? No. What is the expression for time period of simple pendulum? 2 pi root of L by G. Oh, but in fact, what happened? There are a lot of corrections are to be done that we didn't bother. So this will become imperfect in experimental techniques or procedure. So what are the things like what you have to do? You should take care about buoyancy, FB, buoyancy. Neglected. Then next again, viscous drag. will be neglected. Then after viscous drag neglected, then what do we say? Like elongate, elongation and twist in string. Neglected or not noticed, or we don't bother. Then oblique effect of bob. Are you getting? No, the list is. So these are the one thing. These about imperfect in experimental techniques or project. These are one thing. Next, what other things we do is like, from where I should measure the time period. The moment I release, I should measure time period. No, so instead of measuring the time period of oscillations, instead of time taken for 10 oscillations or 10, I'll measure for 9. Next, what happen? I'll measure for some, so like only for 5. All this will become, means if I don't take observations correctly, then also happen that will lead to this one. It all depends upon techniques here. So definitely happen, we should know better ideas. We should have a better picture. Means regarding experiment, how to take reading, we should know. If you don't know that, what mean, it will go to systematic error, not random error. I'm talking about systematic error. So that all will lead to systematic error. Okay, so I think there are still plenty are there. The stopwatch, what you are using, what happened? It should not have any error. You should know how to use that stopwatch. So this all will come imperfect in experimental techniques or procedures here. Next, again, after this, we should also consider the effect of humidity, effect of temperature. As temperature varies, the bob dimensions, it's a metal bob, so its diameter will increase. The string, what will happen, will have some expansion, neglecting. So I'll put it here now. Temperature effects, humidity, wind speed. Even when you switch on fan, what happens? Due to that, air will blow. No, it will also have effect. So all these are neglect. Due to this negligence, what happens? A systematic error will come. Okay, got this. So like this, I think this is a have a lot of things, and so it's not like just directly I'll go lab and I'll do half an hour. We are supposed to think all these things here. So this is about the imperfect in experimental techniques or procedure. Okay, third one is the personal error. Personal error means the experimenter, or I'll call student better, huh? Because you are going to do experiment. The student is not interested, not interested in doing experiment. Not interested. So what is actually needed? You should displace the bob. You should displace the bob and release. The moment you release, you should start counting time. No. So what you do? You release the bob. When the bob is somewhere here or here, you'll start counting time. I think you did error, no? And next what pen? Time taken for 10 oscillations. What is the 1 oscillation? So you're going to release the bob. You go like this. This will be to and fro. One to and fro motion is 1 oscillation. Like that for 10 oscillations, how much of time taken? So instead of observing time for 10 oscillations, what you do? One, somewhere you miss the count, you say, okay, 10 oscillations completed, and you write down. Because there's a personal error. Negligence by the experimental. You will not make observations properly. So these are other things. These are due to environment, other things. You yourself, what happened, are not interested. So actually what happened, the bob has completed 10 oscillations. Then what you say? No, so it completed 9 only. You didn't count properly. And from where you should start counting? The moment you release, you should start counting. But what you do? You are going to release, then what happens, slowly you look at the stopwatch. Then when the bob is somewhere here or here, then you'll start pressing the time button. So I think this particular thing is lost, no? This is called carelessness. So there's one best example I noticed what students when they do in the lab. This one, student not interested, gone. So then plenty of errors will come. You should be what happened, very enthusiastic. You should be very eager to make observation, whether it's a easy or tough experiment. Next, again, before going for that, what you should do, the stopwatch, what happened, is it working or not? You have to check it. Is it having any zero error? Everything, no, all the equipments are there in proper state or not, should be checked it, no? And you should not apply what, like, you should not dip this simple pendulum in water and suspend here and release. You should not do that one. So the apparatus, what happened, should be set properly. Personally, the student not interested in doing experiment. Second one, the student not setting up the apparatus properly. Okay, you should not do one thing. You should do in the lab, no? So you should not you should not hold this pendulum outside the window and oscillate, then wind will be blowing. Then you measure, sir, fresh air I want. That's why I'm just peeking out of the window, poking out of the window, and I'm doing experiment. You should not do. You should not take your arm and pendulum, keep it outside the window, then I'll measure, sir, like I want fresh air. So you should not do that one. And intentionally open, switch on fan and nearby fan, you do it. So all this will come there, that one. The student not setting up apparatus properly or not interested, carelessness. Some student will slip apple in the lab. His friend will be doing. At the end of that, somewhere in between will come, oh, no, you are wrong, something wrong, they'll interfere. So, and not making observation properly, carelessness by the student while doing experiments, not making observation. So all this will come systematic error. Can we minimize systematic error? Yes. You design, you do calibrate properly. And next, the degradation of parts, the parts which got degraded, replace them. Power fluctuations, so use unlimited power supply, something you do that one, zero error. So before using equipment, bring the pointer to zero and start using with this one. And any temperature fluctuations, take care of that. Next, you should know all the methods. Okay, what all I should take care, and you should be interested. So like this, the systematic errors can be minimized here. So there's no doubt about that. We can minimize it. Okay, I get this one. So now, in spite of taking care systematic errors, I think I'll okay, now are you getting? Error is managed by careful experiment, design and manufacture. I think the last sentence I wrote, managed, I'm telling, managed, how to manage. Yes, it is possible in our hand, that one. And the reason is known. The cause is unknown. I think these are the two things which I wanted to stress here of all this. Or one-sided. So some. Okay, now next we'll go for, okay, now student what happen? Okay, you will listen to teacher, you will listen to his physics teacher and you will take care of all the things, then you will do the experiment. Then what he sees that in spite of that, you'll get an error. Then Omi should scold. You will take care of all this, what all I said, no? Okay, you can select he's a very good student and he has obeyed all his teacher instructions and he has eliminated systematic error. So what do you expect? No error, no, but still there'll be error. So what is that? That's a random error. Any reason for that? We don't know. Okay, we'll do one thing. Maybe student has not experienced, so that's why the error has come. So we'll ask teacher. Okay, sir, like the student will ask, sir, like something happened. So can you give me reason for why still I'm getting error? The teacher will say that there's no reason. Then what is the problem? Equipment problem, teacher problem, student problem. The reason for that is unknown. So such errors are called as a random errors. Sir, what is this? Something you are telling very strange things. So what are random errors? I'll put it here. Statistical fluctuations in either direction in the measured data Okay, this one, stat fluctuations in the measured data. The fluctuations are there. Next, again, write it. Usually results from the experimental inability to take same measurement in exactly the same way to get the exact the same number. I think this is something very, very, very important part of the random error. I think books, they have given some definitions. I felt like something you don't get any idea this one. So that's why I just modified it like this. So what you're telling, usually results from the experimenters, usually results from the experimenters inability to take inability. It's a problem with us. It's our inability to take the same measurement in exactly same way. I think I'll bring some commas. Usually in exactly the same way to get the exact the same number. It's my inability what happen to perform the same experiment, to take the same measurement in exactly the same way to get the same number. Sir, what do you mean by that? I'll measure the length of the rod. First time I'll measure 1.153 centimeter. That's what I'm going to give an explanation. Just do listen, and then you can ask answer. Personal error is something different, random error is different. Okay, give me some time. Let me clarify. In the end, you can ask it. Because we are at the beginning of the concept. No? Okay, there's a rod, and I'll bring a scale. I think I have a scale. Huh? This one, let me. No. I will do measurement. I will do measurement here. So how much it is reading? Oh, no, not possible. It will read how much, say like a 0, 1, 2, 3, 4, 5, 6, 6.2. Now what I do is like, I will, then again I'll keep it. Again I'll keep it here. Then it will try to read some other value. Of course, here only one decimal places. Like actually 1 centimeter divided into what? 10 divisions. If you divide 1 centimeter into say 100 divisions or say like 20 divisions, no, then you can see that one. When you measure the length of the rod 2-3 times, no, you're going to get the different value. So what is the problem? The problem is not with the scale. The problem is not with the rod. The problem is with a random error. Why it is, we don't know reason. Exact reason we don't know. This you may not notice if you further graduate scale. 1 centimeter, you divide that into how much? 20 divisions. So like that, you fine tune that one. You make it very small, that one. And when you start measuring, no, different times you'll get different answer. Example, screw vernier caliper. The best thing is like when you just repeat the same thing 4-5 times, no, you're getting different answer. Different readings will come. Why this is? Due to random error. And we don't know reason. But this, so these are the some things are there, that one. So we don't know exact cause for that. I will, this what happens. So with ordinary scale, you say, sir, I measured many times, I get same answer. But you divide 1 centimeter into more number of divisions, no, then you can see that particular thing. Okay, this is about the random error. I'll give further explanation. Random error. This usually due to poor precision. Okay, they are not reproducible. Non-specific causes. We don't know non-specific causes. We don't know the reason for that one. A result is said to be precise if the random error is small. Next we'll go for appear on either side of true value. So average value approaches the true value. Average error decreases. Error is managed by statistical methods. Cannot be eliminated, but can be minimized. That much is what we can say about the random error, that one. So I just wrote all some very important things. So how do, what I do with errors? Errors, what happen? I should manage by statistics here. Means by using statistical methods, I should manage it. First of all, winter, the non-specific causes. Causes are unknown. Causes of error are unknown. I think there's somebody asking, sir, what do you mean by non-specific? I'll write it here. Causes of error are unknown. This is something very important. Are not reproducible. Okay, fine. So this is the now what about the some? Okay, we'll see that we'll compare with the other thing. Suppose this is a true value. True value. There's a x naught. True value. When you do measurement, so it happens one reading x1 will be here, other will be x2, other will be x3. X5, X6. So what happens the reading? What all the measured values are they know? They are the what? Like due to random error, and x naught is true value. So what happened? The measured values, they lie on either side of the true value. So what is this blue color? This blue color line, these are measured values. All right here. X1, X2, X1, X2, X3, X4, X5, and X6 are measured values. Or I'll show using the graph will show it. In the graphical, I'll represent it here. There's a expected value. Then what will happen to the, due to random error, it will be off like this. Look at the values here. They will lie on either side of the true value. No? So the red color is what? True value. And this is the
recent application decision అంటే నడుస్తున్నారు నేను సాయంత్రమే క్లాస్.
Okay, find this one. So this about what about the like a systematic error? Due to systematic error, how it will be? Due to random error. This is due to random error. Measured value. Okay, now I'll draw another curve. Green color, I'll draw it. So look at no. So it is lying on other side, no. So what is this? Measured value. Systematic error. So if I take average, I think it's okay. If I take average, I think definitely I'll approach the red value, no? What about here if you take average? If you take average, where do it will come? It will come here. I think it's far away. So it will not be accurate. I must say, it will not be accurate. It will not be accurate. So therefore, the systematic errors, therefore the problem arises here. So if you have a systematic error, they'll be one-sided. So better to eliminate that one. If you do average, whatever you do, what will happen? Nothing will happen. The systematic errors by taking average will not get eliminated. If you take average, I think I'm the best graph is what I'm giving for students. If you take average of the green color, so you may end up like this. Is it approaching true value? No, if you take average, it not approach true value. For random errors, the measured values that are due to random errors, if you take the average of it, it will approach the red color line. But here, if you take the average, again, what it will be away from the true value only. So therefore, the mathematics will not help to minimize systematic error. What you should do, you should personally come and eliminate that. But random error, what by mathematics, I'm able to manage. That's why I'm saying statistical method. What do you do that? By taking average, everything is called a statistical method. Able to, I think you should have some basic mathematics, which I'm taking help of explanation. So now what happened? Somebody are asking. So when we can conclude that there is no error, there is no experiment in the world till date in the history of mankind where they have done measurement and there is no error. Are you getting? till now in the history of mankind, I'm saying history of mankind, or from the evolution, from the creation till now, there is no measurement which is of error, without error. There will be error. So no question of no error. Random error, systematic error, okay, you can take it, but random error, you can never do that one. Example is the simple pendulum. I'll give one best example. You can try this in home. I think nowadays we have in mobile stopwatch. If you're really interested, you are going to analyze what I'm telling. Or if you just want a rank, okay, you listen my class over. If you really want to become engineer, okay, do experiment. Okay, it's like this. This is the thing. So you take a bob, string, you take it. Sir, Bob, what is there? You go just outside. Eraser, you take it, no problem. Eraser, or any other, some screw, nut, bolt, anything, or some small stone, anything, some rounded object, if you take it, or any square box, anything. Okay, I'll do one thing. I'll put a random object so that you can pick up anything. There's a cotton thread. Plastic wire, anything, let it be. You deflect it. You just deflect it. True value, it's a guess on paperwork. True value is a guess on a paperwork. On paper, true value. In the designing, the true value will be made a guess. Science laws, no? By using laws of science, no, you deflect it. So first what happen? You calculate the time, number of, I'm just giving example of random error, number of oscillations. This is the time taken. First experiment. And for 10 or so like for 30 oscillations, you are going to measure time. And you are going to say like, let it take some around 22 seconds. Next again, for same 30 oscillations, it will take some, say like 24 seconds. Next you repeat 30 oscillations, it will take say some 21 seconds. Next for another 30 oscillations, it may take even up to 19 seconds. So what is this? We don't know. Random error. You can try, you have stopwatch, you can try that one. Don't do for one oscillation. Minimum 30 you should take. That's what we say. Well, why the difference is coming, sir? Same mobile, same string, same everything. We don't know reason. Why the time taken for the same 30 oscillations? It's not that I'm changing this number of oscillations. What do you mean number of oscillations? What do you one oscillation? To and fro, one to and fro motion. Like that 30 times. How much of time it take? I'm just giving rough idea. You do it, you'll get different answer. The reason for that, we don't know. These are the observations. Huh? First observation, second, third, fourth, fifth. Why they're different? We don't know. There's a random error. So what is the reason we have to give? Due to random error. That's all, finished. Any reason for that? We don't know. Then what shall I do? I'm going to take the mean of that as like that the random error will be minimized here. Got the idea? So now our focus is what? Like systematic error, okay. We can manage everything. The random error is something is what I should take it. What mathematics? Yes, I'm going to bring mathematics here. So first here like a measurement of random error. So first I'll measure the readings. This will be, I will take the observations x1, x2, x4, x5, like this, xn. These are the observations. These are the measured values. Then what I do, I'll take the mean of that. So this called like a mean average. Mean average or average value. So this will be xm symbol x1, x2, x3, so on, xn by n. 10 observations, add that all the 10 values by n. So now what I do is I'm going to find out the error in individual observation. So delta x1, what is this? xm minus x1. Either way, I'm putting mod, I should take difference. What is delta x2? xm minus x2. So on, delta xn is equal to xm minus xn. I will take the now the difference of mean and the measured value. I'll find out the error in individual observations. Then I'll define one mean absolute error. So this is called as delta xm. So this is called like a mean absolute error. So I'm able to express now. Next, relative error. Mean absolute error by mean value. There's no symbol actually for relative error. Into 100, you'll get the percentage error. Into 100 will give the percentage error, that one. Difference is a statistics of sir, why mod means I should go for average, no? Okay, this will be relative error, mean absolute error by the mean value. So like this open we define. So there are, I think, random error I'm able to express in terms of what? Either the mean absolute error or the relative error. Percentage error. Percentage error means into 100 will become percentage error. So like this open, I'm able to express now the random error. I brought some quantities to express, means measurement of random error. Next again, okay, now, well, propagation of errors. So what do you mean by propagation of error? I think for exam, this topic is what very important. Propagation of error means like a, what do you mean by that? Okay, let's do one thing. We know how to add masses, no? M1 plus M2, 2 kg, 3 kg, 5 kg. This is scalar addition. Then we brought vector addition. F equal to say like a 10 Newton at an angle of 30 degrees. How it will be added to 15 Newton at an angle of say 45 degrees. This is what vector addition. So you can't just write 10 plus 15, 30 plus 45. Okay, this will be 25 angle 75. Is it okay? No, vector addition you have to go with, no. For that what we brought a vector addition. So what is this? 10 Newton. Please do understand. So some small basic ideas is what we are trying to introduce here. It is making an angle 10 Newton, 30 degrees. Next, 45 degrees. So this is 30 degrees. This is 45 degrees. This is what 10 Newton. Tell me what is the method? Vector addition. This is what? Scalar addition. Scalar addition. So now what we have is vector addition. Now how to add a quantity which are having error? So definitely there's some math is there. The new mathematics is what I'm going to introduce. Getting the idea? In the beginning of physics, we have introduced a new mathematics called like a how to add quantities which are having direction also. That's what the vector algebra. Just it's algebra, there's a vector algebra. Now, a mathematics involved with quantities having error. That's called like a propagation of error, I'll call it. Means how to add two quantities having error, how to subtract two quantities having error, how to multiply two quantities having error, how to divide two quantities having error. and all other operations, how trigonometry, how I should differentiate, all the total everything. So I should now design a new mathematics, a physical quantities having that is having error. So there is a meaning of this propagation of error. Books, what happened? They just wrote propagation of error. So students are thinking, sir, what we are doing? So shall I say it's like a mathematics involved with mathematical operations of a quantities having error. The chapter name will rename it mathematical operations of a quantities having random error, because it's a random error is something, it's a big headache, no? So systematic error, I'm very good. I'm very good in the sense what happened. I calibrated properly. I purchased the equipment manufactured by very good company so that calibration is eliminated. And it's a standard equipment. So all that instrument errors, everything, measuring techniques, everything, okay, fine. And I'm also very much interested. So systematic error gone, zero, fine, no problem. Random error, which company manufactures, what standard parts you use, and the person who is doing experiment, either scientist, teacher or student, random error will be there. So how to minimize random error? I brought a method just now by taking averages, everything. Now we are going to deal with the mass involved with the random error. Getting the idea, all of you? Because the just a core idea, if you can understand rest all mathematics, you know how to do it. So first addition, let's see that. I'm going to add two quantities. First of all, how to express a quantity having random error. I think this is what needed, no? So suppose say a quantity X, I'm going to add two quantities. The product of that is, okay, we'll take it P. Capital R will make it resultant, no? The resultant of this, sum of these two is A plus B. There's an error in A and there's also error in B. Then how do we express that error? Plus or minus delta I. Now what is delta I? What is E? Mean value. This is mean absolute value. Getting the idea? There's a way of expressing a quantity having random error. The mean value of A plus the mean absolute value of A. So I want random error. What I should do? Delta A by A is what? Random error in A. Similarly, mean value of B is this one and the random error is this one. Y plus or minus. Random error, it will fluctuate on either side of the mean value, no? This will be, because the readings will be on either side. So therefore it will be plus or minus here. So the corresponding error in sum, let it be plus or minus delta R. Similarly, mean value, mean absolute value, that one. Mean absolute error. Okay. Okay, now let's do one thing. So this R gets eliminated, no? So what we get? Plus or minus delta R. Please, for God's sake, don't, sir, like take plus or minus common and write only delta R equal to delta A plus delta B. We are not doing this one. We are searching for error. So it should be expressed like this. There's a wrong convention. Don't write like this. Don't express like this. That's all here. What is this one? Whenever they say find the random error, so what you should do? So will you take difference delta A minus delta B or minus delta A plus delta B? Always open you to express maximum possible random error. Though we write like this, if there's an error in A, you know, error in B, you know, delta AB. Suppose a error in delta A is 0.01. Error in delta B is select 0.03. Error in delta is this. Error in A is delta is this much, and here is this delta B. So what is the possible error? I think there are three possibilities are there. No, one, if I add up both 0.04, that is what delta. There's a one value. What is another value? 0.02. If I take difference, what is another value? Minus 0.04. What is the other value? Tell me like which one you are going to pick up. You are going to pick up these two. We have to always express random maximum possible random error. It's a rule. Please, you have to accept the scientific rules. No way. Why we should do? Because always I will design the equipment keeping maximum possible error, not minimum possible error. So that will be on safer side, no? The equipment what I design, I should design keeping the maximum possible random error, not minimum possible. You should design keeping the maximum possible error. It's fine. You'll be on safer side. Say maximum possible is 0.04. If error occurs this much, good, no? Still you are in limits, safer limits. So therefore, I should design for maximum possible error, keeping maximum possible error in mind. So therefore, it's a practice of always expressing maximum possible error, not minimum possible error. Okay, agree this one? Always don't express like this. There's a one thing. Always express maximum possible random error. So what are this delta E? Mean absolute error in it. So when you add two quantities having random error, what are additive? Shall I say mean absolute errors are additive? Then what will happen to relative error? Relative errors are not additive. Delta R by R is not equal to relative errors are not additive. Mean absolute are additive. So when you add two quantities having random error, the mean absolute errors are additive. Additive, I'm telling this one. What about the subtraction? I think it'll be same, no? Subtraction will be R equal to A minus B. Then the possible error in A will be okay, this will become plus or minus of plus B or so whether you add or subtract, the mean absolute errors are additive. Relative errors are non additive. So I'll conclude here. In addition, for subtraction, mean absolute errors are additive. Relative errors are not additive. Okay, similarly, we'll go for multiplication. So multiplication, I'll take like this. P is equal to AB. So let the error in AB, random error in AB, A plus or minus delta A, B plus or minus delta B. Then error in the product. Let me take okay. and I have water. Multiplication. So shall we take P is equal to AB? No. So this will become 1 plus or minus delta P. 1 plus or minus delta A. Expansion of this. Then plus or minus. Okay, delta A, these are small, so this will become negligible. Already delta is very small. The product of two small quantities will become negligible. So therefore, what do I get? So when you take product of two quantities, the relative errors are additive, but absolute errors are not additive. Similarly, we'll do the division. The corresponding error in A will be A plus or minus delta A. The corresponding error in the division. Okay, this I will. So D equal to A by B will get cancelled. So 1 plus or minus delta D by D is equal to 1 plus or minus delta A by A. 1 plus or minus delta B by B minus 1. As delta B is small, applying binomial expansion. Will become 1 minus plus delta B by B. I think minus or plus or minus will be same. So the expansion of this will be so either you take multiplication or division, mean absolute errors are, the relative errors are additive, whereas the mean absolute errors are not additive. In multiplication division, relative errors are additive. In multiplication and division, there's a key idea. Okay, the mathematics involved, just basic math I'm showing. So we should really explore the all other high level mathematics. There's one simple thing I'm showing it here. Okay, now if there are rise to power, R is equal to A to power of P, B to power of Q. There's a result, no? Result A, P, Q. M and P, I'll write it. If they rise to power, what has to be done? I'll do one thing, time being, I'll just show only these two. So we can extend this later on for other things. Shall we take log on both sides? Log r is equal to log of a to power of m by b to power of m. Log a by b. So log of e to power of m I'll differentiate this dr by, and before this, one more step, m log a n log b. So differentiating this dr by r, m dA by a plus or minus. A negative sign is there, no? So no sir, okay, negative. I'll do one thing, I'll adjust like this. Huh? One more step will write it for your convenient. dB. So this will be plus or minus dr by r. So this will become plus or minus m. Keep it like this only. To send a negative inside and do it, no, so it will end up. So what happened, the one which are raised to power, they'll get multiplied by that much of power, that one. Suppose say here m is 3. The random error will get multiplied by 3 times. I think this will be more dangerous, no? So when I am designing equipment, what will happen? Suppose say the power of an equipment depends on what? Like some output, like a output of refrigerator, cooling effect of a refrigerator, cooling effect of refrigerator depends on what? Depends upon the insulation of the walls. Okay, this is 3 times. I'll put like this one. Then next again, it depends upon the cooling effect. Again, it depends upon the the speed of the fans rotating. So it is like this. These are the major things, no, inside that. The rotating fan, that one, and the gas which is present, and the gas which is present. So now tell me, like for cooling effect, what I should take care here? Which one should be given more priority? The insulation, no? Insulation of the room. If you neglect this, what happen? The 3 times impact will be there. If you take care this, the impact will get multiplied by 3 times. So therefore, for the refrigerator, the cooling effect, what happen? I should give priority for insulation of room. If you insulate it properly, okay, fine. If all your windows, doors are open, what you get? Cooling effect, nothing, no? So this like this, what happen? The cooling effect is expressed like this here. So therefore, whenever they try to install in the bedroom, they give clear instruction. So when you're using this, you should close your windows, put curtains, the walls, what happen? That's why we apply a paper. If you install an AC, what happen? You should apply for the walls paper. Paper is a good insulator, which will not permit the heat to flow. If just a bare wall is there, empty like a wall, okay, you apply paint, lapam, everything, heat will conduct. So therefore, a paper should be posted. So nowadays, good design series papers are there. Then what will happen? Your current bill will come down. So of all, very important, this one. And the gas is a very important thing, no? The cooling gas which is there. So that is also important. But of all this, I cube will be there. So this has to be given highest priority. So when you design the refrigerator, like a air conditioner, no, we have that one. Next again, the rotating blades, the fans, how it will blow the air. Next again, the cooling gas. Remaining all other things will be there. Somewhere it will come here, that one. So of all, this is the highest priority. Like this, when you design equipment, which quantity will have more impact on the end output? That has to be measured now properly, and the error in that should be minimized here. Then your product will become successful. So now I think the power, the one which is multiplied by power, what happened? It has to be taken care properly because it will cause more error. It should be designed properly. Okay, clear this. So now we'll go for some general mathematics, because this is about all we have in a book. They have stopped it here only. Let me let me introduce to other things. So we have y is equal to a sin x. There's a random error. We are discussing random error only. Please keep in mind, we are discussing only random error. there's an error in random error in X. So how that error will get reflected in the Y, and A is a constant time being. There's no error in the A. So I'll differentiate this. Dy is equal to A cos X dx. Now I'm interested in the random error in Y. I'll divide these two. Dy by Y is equal to A cos X dx, A sin X. So dy by Y. Now I think it's a very best equation what I'm bringing here, which will reflect what do you mean by propagation of error. Tell me, like, what you should call this random error in Y. What is this? Mean absolute or mean value of X. And what is this? Mean absolute error. You see that the random error in Y, what will happen? Depends on what? The mean value of X and also mean absolute error in X. It got propagated totally different way. No, earlier we said like relative errors are additive in multiplication, division. In addition, subtraction, only what happened, mean absolute errors are additive. What about here? The random error in Y depends on mean value and also the mean absolute error. So it can propagate in any way. So there's no rule that it should be like this only. Okay, now I'll take this one. So better write any random equation and start searching, differentiate, that's all, nothing is there. So we'll go for logarithms. What about the error propagation here? Dy is equal to 1 by X dx. I'll differentiate this. Dy, I'll divide these two. Dy by Y equal to dx by X log E to the X. So this will be plus or minus dy by Y. No, the random error in Y depends on what? Depends in the random error in X and 1 by log of mean value of X. Let's differentiate this. Dy is equal to e to power of X cos X dx. Then e to power of X sin X dx. Dy by Y is equal to cot X dx. Directly I'm writing, then dx. I'll divide these two. Okay, only dy, no, it is. Sorry, dy by y this is. Okay, we have this much here. So dy by y is equal to the relative error in Y depends on mean absolute error in X and also on the mean value.
Sir, can you one scroll up, sir? Thank you, sir.
Let me give another function. The range will take projectile. And this everyone is familiar with this. There's an error in measurement of speed and angle of projection and also acceleration due to gravity. Let's see that in this case, how things all are related. I'll differentiate this. We do have what here? Three functions, no? So first dr is equal to, with respect to g, will differentiate. So u square sine 2 theta, this will become minus g square dg. Plus now I'll keep u square like a sine 2 theta g as it is. I'll differentiate. This will be 2u du. U square by g. So this will be cos 2 theta 2 d theta. Let me divide dr by r. Dividing this, so this should become plus or minus dg by g plus or minus 2 du by u. Okay, look at this. The relative error in range depends on what? Relative error in g, the relative error in speed, the mean value of angle of projection, and also the mean absolute error of angle of projection. Relative So I think it's not that easy, no? Projectile motion, what we studied. That's why I'm telling this one. When you go to the lab, then the real engineer will come into picture. Not on notebook, everything fine. You can write any exam, you'll get gold medal, everything, you'll get awards, you'll get a rank. You just step outside, do that practically, To do projectile motion, to study that with and minimize error, no, you need 2 days. I think in 2 days we'll finish off our projectile motion chapter, all numericals. Anybody will do on the world on paper, I'm telling this one. Solving numerical is not at all, like it's only 1% in science. 99% is all about the doing that practically. And what happened, all that analysis. So there comes the real test of a science, that one. So don't feel proud that, okay, I know many things, okay, I can manage that, this, that one. So look at this equation will tell you that we don't know anything. Okay, let's take some exponential. So error propagates in a very random way, no, here. Like we have some speed like this, v equal to v naught 1 to power of minus bt, where b is a constant, we'll take it. B is a constant. It will not have any variable. In fact, if you want, you can bring variation there also. What about error? How it propagates in this case? We'll take V naught as one function, 1 minus e to power of minus bt as one function. Or you expand this, nothing wrong. Let's do one thing. So differentiate this dv naught, v naught. So this, if you differentiate, minus b e to power of minus bt dt, then e to power of minus bt as it is, then dv naught. Okay, fine. So this is the now let's bring v. I'll adjust v on. I'll adjust V on both sides. So dV by V will become random error. This is equal to, okay, let's go for next step here. dV naught by this will be V naught. Okay, so this is, I think it has become really in that one. So you can further simplify and express this one. So here, look at what all it is. Something very complicated things will come. No, the random error in V. The random error in V depends upon the random error in dV naught and this quantity if you send it to up or leave it like this and all. So here V naught will get cancels. So let me write one more step. dV by V. It should be like this. B not get cancelled. So B, this will become only e to power of, this will be B dt. Is it okay? And this I simplified. Then this will be plus or minus, you write it. Yeah. I'm showing for all things, not just addition, subtraction. For any mathematical operation, I'm trying to give the answer. That's what I'm trying to do here. dV naught by V naught. Check it. This should be the our. So the random error in final velocity V depends upon this random error in the terminal velocity and also the time, and the mean absolute error in the time, and also again the random error, and also depends upon the mean value. What is T? T is a mean value. Try to see this. T is a mean value. Okay, exponential, logarithmic, trigonometric, the range, all different types of things are brought. So I'll bring one more exponential. So what are variable? The V is variable. T is variable. We have to calculate the possible error in I. Okay, how to express that? So I'm putting variable I naught, Q, K are constant. I is a current. This one, all these are constant here. So I'll proceed with the mathematics. I is equal to okay, there's a one equation. Then if I go for this, this will be I by I naught Okay, agree this. So this what we did is I'll take I naught common and we'll get this one here. So I'll take log on both sides now. This will become QKT. QV by KT. Now I'll differentiate this. What is the derivative of log? This will be DI is equal to I naught into I by I naught plus 1. And here Q by K constant. Vt is there, no? So will become T dV minus V dt by T square. So this will become di. Further, it will become I plus I naught Q by K. This shall we write dV by T minus V by T dt by T. Now the relative error in di is equal to Q this is what we have to express it. So the relative error in high, what is di? Not random error. I'm just writing this one. Mean absolute error in I is equal to, it depends on these quantities. So like if you get exponential, you see that there's another way of solving the problem. Okay, so these are the some propagation of errors. Okay, for all very important. So one thing, let's go back to random error because now you got certain idea. Now I'll put it here. The random error, no? If I take more values, x5, xn, xn I'm writing. What do you mean by that? So more number of observations, what will happen to random error? You must really answer. Instead of 30, one student will do 10 oscillations, he'll measure time. Other will do 20, other will do 30, other will do 40, other will do 50. Tell me like which student will get the nearest value. The error will be minimized. The one who will take more oscillations, no? So therefore, the random error, what happens depends upon how many observations you have. If you have 5, okay, one mean value you get. If you take 10, you get mean value. If you take 20 observations, this one. So shall we put it? And if this is correct, what will happen? The error gets minimized. Again, you say that more values. If you take here 20 observations, 20 delta x1 like this, you'll get it. Then what happen? This will get minimized, no? So therefore, how random error and number of observations, they are inversely proportional. This is what I should put it here. Due to random error. So I'll write it. I think here only will write it. This is a very most important part. The random error is inversely proportional to number of observations. So if you want to minimize error, just take more observations. If you want to minimize random error, you have to take more observations. There's no other way. This one, so I think so many numericals will revolve around this. Okay, getting the propagation of error in books. They have just confined only for addition, subtraction, multiplication, division. But in exams, they are stressing all these things. You should know, like in equations where logarithm is there, exponential is there, trigonometric. Okay, both some like a trigonometry and other things. Then you say exponential. So how that error propagates is what I'm giving example here. So this is what you have to practice. So therefore what I suggest is like, you know enough mathematics, you know how to differentiate, integrate. So what you should do now, just write different equations, different, and differentiate and check for possible random error or mean absolute error. This is what a student has to try here. I'll adjust it here only, the final answer. Okay, that one, I think this will be very challenging for student. Just simple maths, no, nothing is to do. We don't have any concept also you see here. So it just revolves around the basic differentiation. If you know it, no, you think you can manage most of the numericals. I'll wind up the class. I'll update the numericals today. By evening, I'll post it.
Okay, sir. Thank you, sir.
Okay, all of you. Thank you. Thank you very much.
Thank you, sir.
Thank you,
Thank
sir.
you, sir.
Thank you, sir.
Thank you, sir.
Okay, thank you, all of you. Take care. Bye. See you.
Bye, sir.
First recording. Okay, thank you, all of you. Take care. Bye. See you. Okay, there's the smallest error what we can have, that one 0. That is meaning of 1 millimeter accuracy. See, terms are very important here. Is asking now what is the possible error you can commit using this scale, 0.1 centimeter. Okay, fine. So more than that also I do it, but that is a minimum error what you can do it. And wristwatch of 1 second resolution. There's a possible error what you can do it. Instead of saying 50 seconds, you may say 49, or you may say like instead of 50, you may say 49 or 51. There's a possible error what it can happen. But if you say no, sir, instead of 50, I'll say 55, then then it will become what, like systematic error. Are you getting? If the 1 second is a resolution, if you say 49 or 51, it will become random error. But instead, if you say 55, then it's a systematic error. And what we are discussing is a random error here. Sir, what happens if systematic error also comes? I'll take one problem. Okay, now this about. So first we'll look at this expression. T is equal to 2 pi L by G. This will be, so the relative error for this, it should be equal to delta G by, so shall we simplify this? 4 pi square L by T square. So then yesterday's formula, the relative error in G should be equal to plus or minus delta L by L plus or minus 2 into delta T by T. But what to do this 100 oscillations? That 100 oscillations is nothing but n oscillations I'll introduce here. And now you can directly straight away ask questions. How come you bring that n oscillations here? How can you bring that one? So we know the relative error. So this random error is inversely proportional to the number of observations. And what is this n? Here n will stand for time for 100 oscillations of the pendulum is found to be 90 seconds. One oscillation is what? The time period t. And what is delta t? Delta t is 1 second. And sir, what is this 100? 100 is the number of oscillations, like a number of observations. So if you take more observations, the relative error should decrease. So therefore I'm adjusting. Books, they have shown another way. So I straight away, I felt like, because I want to define the definition of random error. So for that purpose, I introduced it. Otherwise, what happened, you should use basic mathematics and you can correlate and you can directly find out delta T by T. But to keep our definition intact, no, that n, I just brought it here. Okay, agree this? This one. Actually, the n, what happened, so some books, they have shown n inside. what do you think is number of oscillations? But I wanted to reflect that random error definition. Random error is inversely proportional to number of observations. So if you take more observations, the random error will decrease. Okay, therefore that n I introduced it here. So in books or pen, n is now there. They've adjusted the delta t by t. I think this will be a little bit, the concept of random error will not be reflected. I think most of the books, what happened, they have just directly shown it. But if you refer some good books on error analysis, no, they'll say that, okay, no, see, whatever that, introduce that n here. So what is delta t? No, let's analyze all one by one. What is delta t? 0.1 centimeter. That 1 millimeter accuracy, sir. But he didn't say it's a, what is delta L we define? Mean absolute error, no, but he didn't say mean absolute error. That what is the possible mean absolute error you can do it? That is called as accuracy here. The terminology is a little bit different here. And next is saying resolution. There's a mean absolute error. How much you can do it? 1 second. So delta t is 1 second. But we don't know time period, no, here. For 100 oscillations, 90 seconds. Then for one oscillation, how much? Okay, that is what t. So shall we put t is equal to 0.9? And what is n? N will stand for number of oscillations. That is 100. Okay, let's substitute all this. And delta L is 0.1 by 20 plus or minus 2. Delta t 1 second by 90. Okay, if you solve this everything, I'm using calculator. Without calculator, you are supposed to tell that one. So it is 0.03. So if you express in terms of percentage, it will be 3%. So therefore, the number of oscillations matters a lot. If you take more number of oscillations, the error will get minimized here. Okay, I think these terms are really very confusion for students. Sir, like, why don't they give directly? This is what you have to be careful.
Sir, T is 0.9 seconds now, sir. You wrote 90 seconds.
Time for 100 oscillations, 90, no? Yes. I think please do look at.
Okay,
It is
sir.
4 pi square.
4 pi square. Now, where do pi square has gone? Anybody answer? It's a constant, no? When you differentiate, so what will be the definition of constant? Will be 0. So therefore, so this particular term, it will not change. Now, why this will change? So, but how come you brought this equation? Yesterday's analysis, you have to do it. So call this is everything alpha. Then d alpha by alpha. What it will be? 0, no? Okay, I think some of you are asking that, sir, like how come 4 pi square where they are gone? So I thought you are g equal to alpha, then dg by g. Okay, what is alpha? Alpha is a constant. So the simplification of this, what do we get? Okay, agree this. But here the number of oscillations you have to introduce here, or else you should calculate this particular quantity. I think let's follow this formula. because our Indian books, they have adjusted that one. I don't think so it will reflect anything concept here. In advance, I think they've asked it 5 times. Their expectation was like the students should think like this, but I don't know, our books, they don't show like this. Even I thought, okay, that one, what our books are saying, everything fine, everything. Okay, you'll get same answer. If you refer, I think in Cengage or integrated book, no? So they have done in the same problem is available where they're not reflecting the 10, but they'll get answer. But the idea of that number of oscillations increases, random error decreases, what happened will not be reflected. And 5 times they asked in advance. I don't know, like maybe they wanted to test you this thing. They wanted to reflect you this particular thing. Okay, number of observations will increase, random error will decrease. That's what they wanted to say very loudly. Okay, these are some questions will be there. So we'll take it few more. Like suppose say if there are now if the percentage error so shall we take a one numerical like this? So what is the percentage error in the y? So dy by y should be equal to plus or minus p into dA by a plus or minus q into dB by b plus or minus r into dc by c. Now, whether the relative error, if this dA by a, so if this is say, I'll say 2%, minus 2%, this I'll say plus 3%, and this let me say like a 4%. Then what is the relative error in y means what you are going to write? Plus or minus 2p% and 3q% and 4%. So what to do with negative sign, whether it's a negative or positive, we should always search for the maximum possible, the maximum possible relative error. Am I right here? So let's say that the value of P is 2. The value of Q is say like a 1 or 3 by 2, I'll take it. And the value of then what is the relative error in Y? P is how much? 2. So shall I write minus 2 or plus 2? Plus 2 only. This is something very important. Intentionally, I'm writing, though it was negative, still I'm writing that one. So that then this will be how much? 4%. 9 by 2, 4.5%. 12%. Total how much it will be? 12, 20 point. Now your task, and what is this, sir? Though it was given negative, you made it positive. If I do like this, let it be negative only. I think these are hard questions where student has to ask themselves. If it is like this, so minus 4, 4.5. I think 12.5 will be the answer. Now, which one will you pick up answer now? There's a maximum possible error, no? And always open, we should search for maximum possible error. Though intentionally in the exam, if they give like this, you should pick up this is the answer, not this answer. The random error should be always expressed for maximum possible value. There's a rule they have made it. So in exams, if they give like this, what happens? Don't solve this one. This is nothing wrong. There's nothing wrong, but the convention says that always express maximum possible random error. So definitely 12.5 is less than 20.5. So therefore, for you, this is correct, but according to rule, this is correct here. Okay, so therefore, I should not say wrong. Not advisable. Based on rules. What is this answer? Okay, I'm using word rule. At least you're able to analyze. See, in books, what happened? One sentence is there in SURMA. The random error should be always expressed in terms of maximum possible value. I think that sentence is enough. The sentence is enough, that one. Why we should think like that? Because there's a convention over. Okay, got the idea? This one? Okay, now we'll go for next. Okay, after getting these errors now, we'll go for significant figures. I think already in chemistry, you might have come across. In physics, we'll try to give some suitable reason.